Hi everybody, we're back again. I'm continuing with the Chapter 2 notes on kinematics, and as you can probably see, I'm here recording for the first time with an actual picture-in-picture, and I am in a band room as well because it's at least quiet in here, but you may hear maybe some violins in the background, I don't know. I am in my own room, but it's not as soundproof as I would like. So anyway, we're picking up with average velocity. And we left off with a concept of average speed, and speed is not direction dependent, so speed can be any which way you want something to be going. But velocity is direction dependent, and we call that a vector. So I'm going to write right on here. I'm going to draw an arrow over that average velocity right there. And that indicates that it's in a specific direction, and that's the difference, as you probably know, between a vector and a scalar quantity. So we have a little bit different notation right here than we did with average speed. First of all, our distance is now what we call displacement, and we indicate that by a delta x, and that really should have an arrow over it as well because the displacement is a vector quantity. It's either positive in that direction or negative in that direction. So it's going to have a positive or negative value. Time is not a vector, it's a scalar quantity, but so I'm not going to put an arrow over top of that. But this is velocity right now, and it really depends on what direction you're going. We're still going to be using meters per second as our units, and we're going to, with that arrow over top of it right there, there and there, that indicates that it's a vector. Sometimes I may forget to write the arrow, but if we're dealing with velocity, it's going to be assumed that it's going to be a vector. By the way, it used to be a d, now it's an x. D meant distance, x means displacement. X means specifically displacement in the x direction. It's not a very good horizontal arrow, but you get the idea. This being, I put my hand right in front of the thing there, that being the y direction right there, we're not talking about that axis right there, we're talking about the x-axis, and so we're talking about a movement or a displacement on that axis. And really having an axis or a coordinate system is really what makes a vector, because you can have a positive motion on that axis or you can have a negative motion on that axis right there. Alright, so if there's a sign in front of it, the sign in front of that displacement right there, it'll tell you what direction it's going. Is it moving in the positive direction or is it moving in the negative direction? Okay, so let's do an example right here. It isn't actually going to be about calculating velocity, but just it's going to be about using the notation and using the terminology that we've talked about so far with regards to velocity. So we've got a particle that is just an object, some sort of object, moving at a constant speed of 5 meters per second, all right, in the positive direction. Now let's look at that for a second. It says speed, and it is a speed, but it's also in a specific direction right there. So that means we can call that a velocity, all right, along an x-axis. All right, so let's actually just draw out an axis right here. Not very horizontal, but that is the x-axis. We'll call maybe that 0. Okay, that's positive, as indicated by the arrowhead, and then just to be redundant, we can put a negative right there. So we've got a particle, we have an object, something moving at a constant speed of 5 meters per second along the x-axis. All right, so here's, oh, I'm sorry, don't want to do that. Let's go, back up. Just delete that whole thing right there. I'll draw my axis again. I wasn't paying attention to what direction it was starting at. So I'm going to put my 0 right there, and that's our positive direction. Okay, and so our particle's position, our starting position right here at t equals 0, that is at 0 time, at the starting time, is x equals 3 meters. Okay, so let's do a little, we'll just call that x initial, that's our initial position, all right, and we can actually say that that's a vector right there, so we'll say that is 3.0 meters, and if you want to put little tick marks on this scale, you can right here, but we're just going to write it in as is. And so we have a time distance, or where we have a time elapsed, so I'm going to write that down. Time is our change in time equals 3.0 seconds. All right, now you might ask me why I put that change in time right there. Well, remember, time is something that hopefully that is elapsed, right? And so if our initial time, oops, I'm not writing, I'm lasering. If our initial time equals 0 seconds, as we're told right here, that's kind of our starting time, all right, then it can be assumed that our final time, t final, would be 3 seconds. All right, so then that means our total elapsed time is 3.0 seconds. So usually time starts at 0, like when you run a mile. All right, you start time at 0. You don't start it in the middle of a minute somewhere. Hopefully you started at 0. So if we're told the elapsed time, like after 3 seconds right here is 3 seconds, then we can just say, hey, all right, our change in time is 3 seconds. Okay, so then that means our where are we right here? Our position at 2 seconds is 3. Okay, so our velocity, our speed, or you might say along the x-axis, the speed in, whoops, come on laser, in that direction is what? Well, we're told that, right? 5 meters per second right here. So we're going to write that down as well. So our velocity, or you might say our average velocity, on average, is 5.0 meters per second. All right, so what we want to find out is what is the particle's displacement, that is, how far has it been moved in those 3 seconds, and what is its final position right here, okay? So let's go ahead and do this. Let's write down what we know about how to calculate velocity. Velocity average equals change in x. Hey, that's our displacement right there, right? Over our change in time. And that's our time, which we know right there. If we're solving for displacement, we just say, all right, oops, get my pen back. Delta x is going to be what? Well, if we wanted to get x all isolated by itself, we're going to take our t and bring it up and multiply it next to the average velocity right there. So that equals average velocity times our change in time, both of which we know right here. So that means our change in x, that is our displacement over that time, is going to be, what is our velocity? 5 meters per second times, what's our elapsed time? It says over here, 3 seconds, okay? 3.0 seconds. So that means our change in displacement, all right, our change in x is going to be, what is that, 15. Oops, it's not a very good 5, is it? I'll just erase that right there. 15 meters. All right, now how do I know it's just meters? Well, first of all, I know displacement is a distance, right? So it should be just meters right here. And the other thing is this. I can say, okay, I've got meters per second times seconds. So the denominator seconds here and the numerator seconds here cancels out. So they go away, and all I'm left with is an answer just in meters right there. So that's my final answer for the first part. That's my displacement. All right, delta x is 15 meters. So the question is then, what is the final particle's final position right here? All right, where does it end up? Okay, well, we know from a couple days ago that change in position equals the final position, all right, minus the initial position right here. Okay, and if we want to solve for this, that means we get it all by itself, so that means we're going to add delta x, or displacement, plus x initial, and that's going to tell us what our final position is right there. Okay, so sorry, it's getting kind of squeezed in down at the bottom right there. So we take what's our displacement? We just found that a minute ago, right? That's this right here. So 15 meters plus what's our initial position? Well, we're told that right here. Okay, 3 meters. And I think you know where this is going. 3 meters is going to equal our final position. So that would be 18 meters. That is x, getting squeezed in down here, x final equals 18 meters. And that makes sense because if you move 15 meters, but if you start at x equals 3 meters, so you move 15 meters that way, that means your final position is going to be 18 meters. Let me add those up. Okay. All right, so let's take a look at something called instantaneous velocity right here. What instantaneous velocity is the velocity at any one point along a certain axis. Okay, and if we're talking about an axis, let's think of something moving in a straight line, like let's say a dragster. Okay, they don't turn very much; they're moving hopefully in a straight line down the track. All right, well, you know that they don't. Oh, there was a bell. You know that they don't go the same speed all the time. The whole excitement of drag racing is that they go from stop, and they go faster and faster and faster, so the speed keeps changing. But the instantaneous velocity, this right here, is the idea of its speed at any one point. All right, so it's moving at a constant velocity or uniform velocity, and that means the average speed and the instantaneous speed or velocity would be the exact same thing. All right, because it's moving at a constant rate like that, and so at any one point it's going to be the same speed or the same velocity. But if it's not the same, if it starts from rest, for example, and then it moves along, gets faster and faster and faster and faster and faster, well, there you could think of like moving from this point to this point right here and going some distance over time, and there is an average velocity, but it's not the same as the velocity at any one point, because the velocity at any one point, starting here and going slow and then faster, 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 that velocity constantly changes. All right, so in that case, you would not have the same instantaneous velocity as the average velocity. They would be different. And if the velocity has changed, we call that acceleration right here, and that we'll get into a little bit later.